All right, let's jump right in. Shaggy Dog Spectrality. I know, it sounds kind of weird, maybe even a little silly, but I promise you, if you stick with me, we're about to unpack a really beautiful and powerful mathematical idea that shows us a hidden pattern in all sorts of complex systems. So first things first, let's make sure we're all on the same page. We've all heard a Shaggy Dog story, right? It's that joke that goes on and on and on. It's full of all these side plots and random details, and you're waiting for the big payoff. But the punchline is, well, it's completely pointless or anticlimactic. It's all about the long, rambling journey, not really the destination. But here is the big question, the one that this whole explainer is built around. What if that structure, that really long, complicated journey that leads to a super simple, almost trivial ending, what if that isn't just a recipe for a bad joke? What if it's a deep, fundamental principle for how the universe actually works? Well, that's exactly what this research gets into. It basically says that this narrative structure, the elaborate path to a simple ending, isn't just a quirky storytelling device. No, it's a fundamental blueprint that actually describes how a whole bunch of real, complex mathematical and even physical systems evolve over time. So the key idea is that we can split these systems into two different parts. On one hand, you've got the elaboration. This is the journey part. It's complex, it's winding, it's full of what seem like digressions. This is the transient stuff, the part that eventually just fades away. And on the other hand, you have the punchline. This is the destination. It's simple, it's rigid, and it's totally unchanging. It's the final, stable state that the system is always inevitably gonna reach. And this isn't just some small niche idea. This pattern pops up in all sorts of surprisingly different places. Now, don't worry if these terms sound super technical. Think of it like this. It describes everything from the random path a particle takes through a complicated maze, to the logical steps in super abstract algebra, and even how systems can get kind of stuck in a temporary state before finally settling down. The point is, in all these different fields, you see the same Shaggy Dog pattern over and over again. Okay, so how do we actually see this pattern in the math? Well, the secret lies in something called spectral theory. A good way to think about it is like using a prism to break white light into a rainbow. We can do the same thing with a complex system. We can break down its behavior into its most basic components, its spectrum, to really understand the story it's telling. And to do that, mathematicians use this amazing tool they call a Shaggy Dog operator. Think of it like a special pair of glasses. When you look at a system through these glasses, its spectrum just cleanly splits into those two parts we've been talking about, the simple, dominant punchline and the rich, messy, fading elaboration. And this visualizes it perfectly. Imagine you're looking at a graphic equalizer for a sound system. The dominant spectrum on the left, that's like one single, loud, deep bass note that just keeps going and going. That's the punchline. It's stable. It never goes away. Now, the peripheral spectrum on the right, that's like all the other complicated bits of the music, the high notes, the little echoes, the harmonies. They make the song interesting for sure, but they all eventually fade out. So here it is, laid out nice and clear. The dominant part of the spectrum, with its one stable peak, is the punchline. And that peripheral part, with all its many fading signals, that is the long, winding elaboration that eventually dies down. The story and the math, you see, they're just perfect mirrors of each other. Okay, now this is where things get really, really mind-bending. The most powerful, most surprising part of this whole idea isn't just that these two parts exist. It's that the punchline is unbelievably robust. So let's just walk through it. Imagine we start with a really simple system that has a clear, predictable ending. Now, let's add a digression, a little side loop, some extra complication. What happens? Well, the journey, the elaboration, it definitely gets longer and way more complex. But, and this is the absolute key, the final ending, the punchline, it stays exactly the same. I mean, this quote really just says it all, doesn't it? You can make the story as shaggy as you possibly want. You can pile on layers and layers of complexity, side quests, and distractions, and yet none of it will change the fundamental outcome. And get this isn't just a neat little observation or a coincidence. It is a mathematically proven theorem. The stability of the punchline is literally guaranteed. It's basically immune to any changes you make to that messy, transient, elaborative part of the system. It's rock solid. So let's zoom all the way out for the big finish here. What this research is really showing us is that the Shaggy Dog story isn't just a funny little analogy. It's a universal blueprint for understanding how complexity works across huge domains of mathematics. This table, right here, this is the real aha moment. It shows how this one simple idea connects all these seemingly separate fields. So let's just quickly walk through it. For random walks, the story is a particle just wandering around all the complicated side paths of a network. The punchline, it eventually settles into a predictable average location. For narrative automata, think of them as simple robots. The story is them getting caught in all sorts of digression loops, but the punchline is that final, inescapable state they were always programmed to reach. And even in something as abstract as spectral sequences, the story is a whole mess of complex calculations on intermediate pages. The punchline, it all collapses down to a simple, clean answer on the very last page. It is the same exact pattern, hidden in plain sight, everywhere. So, if you take just one thing away from all of this, let it be this insight. A system's true character, its essential nature, isn't found in its chaotic, complex journey. It's found in its simple, stable, and inevitable destination. And that leaves us with a pretty wild final thought to chew on. Think about things like the stock market, or biological evolution, or even how ideas spread online. What if all of these incredibly complex systems we're trying so hard to understand are, at their very core, just really, really, really long Shaggy Dog stories, all heading towards a simple punchline that we just haven't been able to see yet?